Assalamualaikum warahmatullahi wabarakatuh, and hello doctor. So we are all from section 2. We do the experiment of M2, which is the Hall effect. Our group are Ivan Chong Kai Hong, Siti Nofariza Fahana, and me is Nur Ain Syafiqah binti Muhammad Yusuf. So in this video, all of us we're gonna talk about the introduction, objective, methodology, data collection, and discussion of the experiment. So, the objective of this experiment is to determine the carrier density NOP and carrier mobility in germanium Ge. So next, we continue to the introduction of this experiment. The introduction of this experiment is about the Hall effect. So what is the Hall effect? Hall effect is when a magnetic field is applied at right angles to the current flow in a thin film where an electric field is generated. It is mutually perpendicular to the current and the magnetic field. Magnetic field is directly proportional to the product of the current density and the magnetic induction. After that, we continue to the methodology of this experiment. First thing first, the apparatus that we use in this experiment is Hall probe, which is GL crystal, Hall effect apparatus, electromagnet, constant current power supply, and also digital gauge meter. And then the current IX was adjusted. So next is the procedure of the experiment. So first, we start with the Hall probe was set to voltage and current respectively. Second, the Hall effect apparatus was switched on, and then the current IX was adjusted. So next, the Hall voltage were measured for both direction, which is current and also magnetic field. So the Hall voltage of VH, a function of current IX, and the Hall voltage of VH, a function of magnetic field BZ, were measured, which is for the voltage of VH, function of current IX, we keep the magnetic field BZ constant, and the next Hall voltage VH, which is a function of magnetic field BZ, we keep the current IX constant. So lastly, the magnetic field BZ by the gauge meter was measured.
Okay, so for this part, this is for data collections. Here is for part 1. So the value for B is 50 gauge. There is current, coil 1 and coil 2. And coil 1 and coil 2 value is divided by 2, which is for positive and negative value. Here is the data for part 2. So as you can see, I equal to 3 milliammeter, and then we got value for B, coil 1 and coil 2. Also, coil 1 and coil 2 is separated by 2 value, which is positive and negative, same as before. Now we are in data analysis part. So as you can see, there is 2 different columns here, which is for magnetic field and then the average Hall voltage. So how did we calculate the average Hall effect? So by using the first formula that we wrote at the first point, it is the formula to calculate the average Hall. So C1 and C2 here is referred to the coil 1 and coil 2, where the positive and negative sign here is referred to the positive and negative value. Why we divide by 4? It is because for each coil we got 2 different readings, so the total up is 4. Next, at the right hand side of the average Hall effect value, there is the uncertainty. So we calculate the uncertainty by using the second formula that we wrote at the second point. So that is the formula. After that, we plot the graph for Hall voltage versus magnetic field. as you can see, the Hall voltage is increasing as the magnetic field increase. So we conclude that the magnetic field is proportional to the Hall voltage. So at the right hand side, it is a value for gradient and y-intercept that we obtain from the graph. So the m value is 0.06 and the uncertainty is 0.001 mvt to the power of -1, while the c value is 93 and the uncertainty is 0.2 mv. Okay, so for this part, this is for Hall coefficients RH, which is RH equals to 1 per NE. So by using the formula of N, we make NE as a subject and then substitute the NE formula into the RH formula, and then same goes to before. For the M, we also substitute the M formula into the RH formula, and we will got the new formula, which is RH equals to negative MD divided by I. By substitute all the value that we got from the past calculations into the RH, we got the value for RH. Next, same as before, we need to calculate the uncertainty as well. So by using the formula of uncertainty of RH, we substitute all the value and we got the uncertainty, which is 0.16 times 10 to the power of -6. For question number 2, we were asked to determine the type of majority charge carriers and whether the crystal is N-type or P-type. So we would say that the crystal is N-type because the Hall coefficient, which is RH, is negative in value. So the majority charge carriers is free electrons. Next, for question number 3, we were asked to calculate the charge carrier concentration density, which is N. So by using the N formula, which is N equal to 1 divided by RHE, we substitute all the value for RH and also the E. After that, we got the value for the N, and then we need to find the uncertainty as well. And then by using the formula of uncertainty, which is delta N, we rearrange the formula and then we substitute all the value and then got the uncertainty for N, which is 0.1 times 10 to the power of 23. For question number 4, we were asked to find the carrier mobility, which is micro. So by using the formula of micro, which is micro n equal to RH sigma. From the past lab, we already know the value for the rho. So we just substitute the value in the sigma formula. And then after that, we substitute back in the micro n formula, which is micro n equals to RH sigma. And then the value that we got for micro n is negative 9.55 times 10 to the power of -5. And then for the uncertainty, we need to rearrange the uncertainty formula to find the uncertainty of micro n. And then substitute all the value, and then the answer is 0.16 times 10 to the power of -5 for the uncertainty.
For the discussion, the first part, determine whether the semiconductor is N-type or P-type. How to determine whether a semiconductor is N-type or P-type? From the equation from the manual, it's supposed that the semiconductor is N-type, because as we can see in the manual formula, N or P is equal to negative Bi over VDE. The negative suppose that the semiconductor is N-type. In order to determine whether it is N-type or P-type, we would need to go deep in the understanding of the apparatus setup. We are required to understand the direction of the current and the magnetic field. But from the experiment, we cannot see clearly whether of the setup of the experiment. Hence, it is hard to determine the direction of the current and the magnetic field. From using the Fleming right-hand rule, we can determine the N where negative charge carried in the N-type semiconductor. Before going deep into the understanding of using Fleming right-hand rule, we must understand the characteristic for N-type and P-type semiconductor. In the first diagram, if a magnetic field is applied to an N-type semiconductor, both free electrons and holes are pushed down towards the bottom surface of the N-type semiconductor. Since the holes are negligible in N-type semiconductor, so free electrons are mostly accumulated in the bottom surface of N-type semiconductor. This produces a negative charge on the bottom surface with an equal amount of positive charge on the upper surface. So in N-type semiconductor, the bottom surface is negatively charged and the upper surface is positively charged. As a result, potential difference is developed between the upper upper and bottom surface of the n-type semiconductor. In the n-type semiconductor, the electric field is primarily produced due to the negatively charged free electrons. So the Hall voltage produced in the n-type semiconductor is negative. For p-type semiconductor, same. If a magnetic field is applied to a p-type semiconductor, the majority carriers, which is the holes, and the minority carriers, which are the free electrons, are pushed down towards the bottom surface of the p-type semiconductor. Free electrons are negligible, so holes are mostly accumulated at the bottom surface of the p-type semiconductor. So the p-type semiconductor will have positively charged at the bottom surface and negatively charged at the upper surface. As a result, the potential difference is developed between the upper bottom surface of the p-type semiconductor, resulting Hall voltage which to be positive. Hall effects also helps to determine the type of material. We can easily identify whether a semiconductor is p-type or n-type by using Hall effect. If the voltage produced is positive, then the material is said to be p-type, and if the voltage produced is negative, then we said it is to be an n-type semiconductor. For part 2, for discussion, I will discuss about graph of the Hall voltage V vs the magnetic field B. From the graph, we can see that it is increasing linearly. The higher the magnetic field, the higher the Hall voltage produced. So from the formula given below, which is Vx equals to Bz, which is, we can see it is directly proportional to Bz. So where the charge density will be much higher at the end of the semiconductor when the magnetic field increases. Okay, when the magnetic field increased, resulting to a higher potential difference between the two ends due to the increase in the charge carrier concentration at both ends. To add on about this part, they have given us the formula Vx NOP is equal to negative Bz Ix over dE, is saying that this semiconductor is n-type, and they were expecting us to get a positive gradient graph because the setup of the apparatus of the voltmeter is a fact to understand the direction of whether the negative charge carrier is at the bottom side or at the top side, and we are not sure about the setup of the experiment and the direction of the current together with the magnetic field. So it is a very considerable formula for us to refer. For the third part, weakness of the experiment, students are unsure of the experimental setup and they were unable to use Fleming's right-hand rule because they don't know the direction of the magnetic field and the current. The third one is we are unsure that the direction of the voltmeter to determine whether it is n-type or a p-type semiconductor.
Next, we continue to the question and answer. First question is, what is Hall effect? Hall effect is the production of voltage difference, which is a Hall voltage VH across an electrical conductor that is transverse to electric current in the conductor and the magnetic field and perpendicular to the current. So the next second question is about what are n-type and p-type semiconductors. N-type semiconductor is extrinsic. N-type semiconductor is extrinsic semiconductor doped with extra electron donor. P-type semiconductor is extrinsic semiconductor doped with material missing electron, which produce hole as acceptors.
Question number 4. Do the holes actually move? Holes are positive charge carriers and hole does not move. As you can see in the diagram, the green circle represents the electron and the dotted circle represents the hole. Both are moving in the opposite direction, where the electron moves to the right and the hole moves to the left. For an example shown in the diagram below, silicon with 4 valence electrons is doped with 3 valence electrons. The hole is formed in the covalent bond. The trivalent atom may borrow an electron from an adjacent silicon atom to form 4 covalent bonds. Hence, this leaves a hole in the silicon. Hence, the holes are filled by the movement of electrons, showing that the holes are moving in the opposite direction of the electron. For question number 5, show that carrier concentration NOP is equal to negative Bi over VDE. From the first equation, E equals to VB, Hall voltage is equal to E dy. sub 1 into equation 2. Whole voltage is equal to VB dy. The current equals to NAVE. Vx is equal to current over NAE. Sub equation 6 into equation 4, we would get whole voltage is equal to VDI over NAE. N is equal to VDI over VDDE. But we can cancel at the next equation where dy cancel, we would get N equals to VI over VDE. Hence, we would get the equation. But the negative sign is assuming that the semiconductor is N-type. Equation 6 says that while the resistance of the sample increases with the increase of the magnetic field, as we can see the equation below, the whole voltage is equal to Vx Bz dy, showing that V, the whole voltage, is directly proportional to the magnetic field. Hence, when the magnetic field increases, the whole voltage increase. We can use V equals to IR to prove that the magnetic field is directly proportional to the resistance too. Hence, we can also know that when the magnetic field increases, the concentration of charge between the two ends also increases. The both ends will result in a higher potential difference.
For question number 7, we will ask why a high input impedance device is generally needed to measure the Hall voltage. So the answer is a high input impedance device will give us a minimum current. This is to ensure the accuracy of the results we obtain later. The current usually will flow through the electrical device instead of infinite resistance path. It will happen when a high device is connected in parallel to the sample. Next, for question number 8, why the Hall voltage should be measured for both directions of current as well as of magnetic field. So we answer that it is to get the accurate value or result in calculating the value for the average of Hall voltage and the Hall voltage itself. In one situation, like if the magnetic field is applied across the conductor while the voltage is set up to the separation charge, like there would be a thermoelectric effect will happen. So the thermoelectric effect can be reduced by reversing the polarity of current flow and magnetic field.
In conclusion, the current density N is equals to negative 6.53 plus minus 0.11 to the power of 93 per meter cube. The current mobility mu supposed to be positive, as current mobility will only have positive values, which is 9.55 plus minus 1.6 to the power of negative 5 meter square V per second.